Tonight, we're going to shrink down to a scale so small that it breaks everything you think you know about reality. We're going to explore the true size of a single atom. And here's what's going to shock you. An atom is almost entirely nothing. The solid ground you're standing on, the chair you're sitting in, your own body, all of it is made of atoms that are overwhelmingly empty space. If you could remove all the empty space from every atom in every human on Earth, all 8 billion of us would fit inside a single sugar cube. That's not an exaggeration. That's physics. And by the end of this journey, you're going to understand exactly why the universe you touch and feel is built from almost nothing at all. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already understand. Your hand. Hold it up in front of you and look at it. Spread your fingers and study them for a moment. You can see the lines on your skin, the ridges of your knuckles, maybe a few tiny hairs. Your hand feels solid. It looks solid. If you press it against a table, it stops. The table pushes back. There's no ambiguity. Your hand is a real, physical thing, made of real, physical stuff. You've used it your whole life to grab things, to feel things, to interact with the world around you. It's one of the most familiar objects in your existence. But here's the thing most people never think about. Your hand is made of atoms, and atoms are unimaginably small. So small that no human sense can detect a single one. You can't see an atom, you can't feel an atom, you can't hear one, smell one, or taste one. Every sensation you've ever experienced, every texture, every temperature, every moment of contact between your body and the outside world, all of it has been the collective behavior of trillions upon trillions of atoms acting together. Not one single atom has ever registered on your senses individually. They're simply too small. So how small are we talking? Let's build up to it, because jumping straight to the size of an atom doesn't work. The number is so small that it means nothing without context. We need to start with things you can see and understand, and then shrink step by step until we arrive at the atom. And I promise you, by the time we get there, you'll realize that the word small doesn't even begin to cover it. Let's start with something you can see easily. A grain of sand. Pick one up at the beach and hold it between your fingers. A typical grain of sand is about 0.5 millimeter across. That's small by everyday standards, but you can still see it. You can feel it. You can roll it between your fingers. Your eyes can make out its shape, maybe even some detail on its surface if the light catches it right. It's tiny, but it's within the range of human perception. Millimeter is 1,000th of a meter. You can see things that are a millimeter across without any trouble. The tip of a sharpened pencil, the thickness of a credit card, the width of a single strand of thick thread. These are all roughly in the millimeter range. Your eyes handle these sizes just fine. But now let's go smaller. A human red blood cell is about 7 micrometers across. A micrometer is 1/1,000,000th of a meter. That's 1,000 times smaller than a millimeter. You absolutely cannot see a red blood cell with your naked eye. It's invisible to you without a microscope. And yet, red blood cells are enormous compared to what we're heading toward. There are about 25 trillion red blood cells in your body at any given moment, each one carrying oxygen from your lungs to your tissues and bringing carbon dioxide back. They're doing this right now as you listen, flowing through your veins and arteries in an endless circuit, and you can't see a single one of them. They're too small. A bacterium is even smaller. A typical bacterium like E. coli is about 2 micrometers long. That's roughly 3 times smaller than a red blood cell. Bacteria are so small that thousands of them can fit on the period at the end of a sentence. You've probably swallowed millions of bacteria today without knowing it. They live on your skin, in your gut, on every surface you touch. There are more bacteria in your body than there are human cells, and yet each individual bacterium is completely invisible to you. A virus is smaller still. The influenza virus is about 100 nanometers across. A nanometer is 1 billionth of a meter. We've now shrunk 1,000 times from the micrometer scale. A virus is so small that it can't even be seen with a standard optical microscope, the kind you might have used in a school science class. Those microscopes use visible light to illuminate whatever you're looking at. But visible light has a wavelength of roughly 400 to 700 nanometers. That means visible light waves are physically larger than many viruses. The light literally passes around the virus without interacting with it properly. It's like trying to detect a pebble by throwing beach balls at it. The beach balls just roll past. You'd never know the pebble was there. To see viruses, you need an electron microscope, which uses beams of electrons instead of light. Electrons have much shorter wavelengths, allowing you to resolve much smaller objects. And still, we're not at the atom yet. We're not even close. An atom is about 1/10 billionth of a meter across. Written as a decimal, that's 0.1 nanometers, or 1 angstrom. Let me put that another way. If you took a single meter, 1 meter, and divided it into 10 billion equal parts, each part would be about the width of an atom. 10 billion. That's not a number your brain can easily process. Let me try to make it real. If you lined up atoms side by side, you'd need about 10 million of them to span the width of a single millimeter. 10 million atoms in a row just to cover a distance you can barely see. The head of a pin is about 1 millimeter across. 10 million atoms lined up shoulder to shoulder across the head of a pin. If each atom were the size of a marble, that line of marbles would stretch about 100 kilometers. 100 kilometers of marbles just to represent the atoms spanning 1 millimeter. A human hair is roughly 70 to 100 micrometers thick. That means you could line up about 500,000 atoms across the width of a human hair. 500,000 atoms. And remember, a human hair is already something most people consider thin. It's something you can barely feel between your fingers. 500,000 atoms across its width. Each one far too small to see, to feel, or to detect in any way with your unaided senses. Now, let's think about atoms in 3 dimensions. Not just lined up in a row, but packed together, filling space. Because that's how atoms actually exist in the real world. They're not arranged in neat single-file lines. They're packed in every direction, filling volume. And when you start counting atoms in everyday objects, the numbers become almost incomprehensible. A single drop of water, a tiny droplet hanging from the tip of a faucet, contains approximately 5 sextillion molecules of water. That's 5 followed by 21 zeros. And each molecule of water is made of 3 atoms, 2 hydrogen and 1 oxygen. So that one little droplet contains roughly 15 sextillion atoms. 15 followed by 21 zeros. In a single drop of water. You could watch drops of water fall from your kitchen faucet for the rest of your life, and never once suspect that each drop contains more atoms than there are grains of sand on every beach on Earth. The number of grains of sand on all of Earth's beaches is estimated at roughly 7.5 quintillion. That's 7.5, followed by 18 zeros. And the atoms in a single drop of water outnumber that by a factor of about 2,000. Think about that for a moment. Every grain of sand on every beach on every continent on Earth, and the atoms in one tiny droplet outnumber them all by an almost incomprehensible margin. And the observable universe contains a staggering number of stars, roughly 200 billion trillion. A single drop of water doesn't quite reach that number, but it comes remarkably close, within an order of magnitude. The point is that even in something as small and ordinary as a water droplet, the number of atoms is of a cosmic scale. Your body contains about 7 octillion atoms. That's a 7 followed by 27 zeros. 7 billion 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 atoms. Each one too small to see, too small to feel, working together to create you. The vast majority of these atoms are hydrogen, oxygen, and carbon. Hydrogen is the simplest and smallest atom. Carbon is the backbone of organic chemistry, the element that makes complex life possible. Oxygen keeps you breathing. These 3 elements, along with smaller amounts of nitrogen, calcium, phosphorus, and trace amounts of many others, combine to form every molecule in your body. Your DNA, your proteins, your bones, your blood, your brain, all of it. 7 octillion atoms arranged in specific patterns, held together by electromagnetic forces, forming the structures that allow you to think, to move, to exist. And here's what's remarkable, not a single one of these atoms is alive. An atom of carbon is just an atom of carbon. It has no awareness, no purpose, no life. A hydrogen atom pulled from your body is identical to a hydrogen atom floating in interstellar space, or sitting inside a star. There's nothing special about the atoms themselves. What makes you alive is the arrangement, the way those atoms are organized into molecules, and those molecules into cells, and those cells into tissues and organs. Life is a pattern, not a substance. The atoms are just the building blocks, and those building blocks are unimaginably small. Now here's something that might bother you if you think about it too long. Atoms are so small that we can't actually see them in the traditional sense. We never will be able to see them with our eyes, no matter how good our eyesight is, no matter what kind of corrective lenses we develop. This isn't a limitation of our technology. It's a limitation imposed by physics itself. Seeing something requires light to bounce off that object and enter your eye. But visible light has a specific range of wavelengths, roughly 400 to 700 nanometers. An atom is about 1/10 of a nanometer. Visible light waves are thousands of times larger than an atom. Trying to see an atom with visible light is like trying to feel the shape of a marble using ocean waves. The waves are so much bigger than the object that they just wash over it. No detail is preserved, no image is formed. The atom is invisible, not because it's hiding, but because the tool we use to see visible light is fundamentally incapable of resolving something that small. It's the wrong tool for the job. This means that for most of human history, atoms were purely theoretical. The ancient Greek philosopher Democritus proposed around 400 BC that all matter was made of tiny indivisible particles he called atomos, meaning uncuttable. It was a remarkable intuition, but it was just philosophy. He had no evidence. He couldn't see atoms or measure them. He simply reasoned that if you kept cutting something into smaller and smaller pieces, eventually you'd reach a piece so small it couldn't be cut anymore. For over 2,000 years, this idea remained controversial. Many great thinkers rejected it entirely. Aristotle, whose ideas dominated Western thought for centuries, didn't believe in atoms. He thought matter was continuous, that you could keep dividing it forever without ever reaching an indivisible particle. It wasn't until the early 1800s that the atomic theory began to gain real scientific support. John Dalton, an English chemist, proposed in 1803 that elements were made of identical atoms with specific weights. He showed that chemical reactions could be explained by atoms combining in fixed ratios. Dalton couldn't see atoms either, but he could infer their existence from how chemicals behaved. His work was a crucial step, but atoms were still invisible, still theoretical, still just an idea that happened to explain the data. Throughout the 1800s, evidence for atoms accumulated. The study of gases, of chemical reactions, of electricity flowing through solutions, all of it pointed toward matter being made of tiny, discrete particles. Ludwig Boltzmann developed a mathematical framework showing that the behavior of gases could be explained by the motion of enormous numbers of tiny particles. His work was brilliant, but he faced fierce opposition from scientists who thought atoms were just a useful fiction, a mathematical trick rather than a physical reality. Boltzmann died in 1906. Tragically, just as the scientific community was beginning to accept that atoms were real. In 1905, Albert Einstein published a paper on Brownian motion, the random jiggling of tiny particles suspended in water. Einstein showed mathematically that this jiggling could be explained by the particles being bombarded by water molecules, which were themselves made of atoms. Jean Perrin later confirmed Einstein's predictions experimentally, providing some of the strongest evidence yet that atoms were real physical objects, not just theoretical constructs. By the early 20th century, the existence of atoms was firmly established, but no one had seen one. No one would see one for decades. The first real images of individual atoms came in the 1950s and 1960s with the development of the field ion microscope by Erwin Müller. This instrument could resolve individual atoms on the tip of a sharp metal needle by ionizing gas atoms near the surface and projecting them onto a screen. It was crude by modern standards, but it worked. For the first time in human history, people could see the arrangement of individual atoms. But the real revolution came in 1981 with the invention of the scanning tunneling microscope by Gerd Binnig and Heinrich Rohrer at IBM's research laboratory in Zurich. This instrument works on a completely different principle. It uses a needle with a tip so sharp that it ends in a single atom. This needle is brought incredibly close to the surface being studied, just a few angstroms away. At this distance, electrons can quantum tunnel between the tip and the surface, creating a tiny electrical current. By scanning the tip across the surface and measuring how this current changes, the microscope can map the surface with atomic resolution. The scanning tunneling microscope didn't just let us see atoms, it let us manipulate them. In 1989, Don Eigler at IBM used a scanning tunneling microscope to arrange 35 individual xenon atoms on a nickel surface, spelling out the letters IBM. Each letter was about 5 nanometers tall. This was the first time humans had deliberately positioned individual atoms. We went from not even being sure atoms existed to literally picking them up and putting them where we wanted in less than 2 centuries. Those images from scanning tunneling microscopes are stunning. They show atoms as tiny round bumps arranged in regular patterns on surfaces. If you look at an image of atoms on a gold surface, for example, you see neat rows of tiny spheres packed together like oranges in a crate. Each sphere is a single gold atom. They're so small that millions of them fit in a space smaller than the width of a human hair. And yet, there they are. Visible, real, physical objects arranged in patterns dictated by the forces between them. But remember, these images are not photographs in the traditional sense. No light was involved. The microscope is measuring electrical currents and translating them into images. We're not seeing the atoms the way you see an apple on a table. We're detecting their presence through their electromagnetic properties and then creating a visual representation. The atoms themselves remain far too small for light to reveal. Let's try one more approach to understanding atomic size, because I think this comparison really drives it home. Imagine you're holding a blueberry, a regular blueberry about 1 centimeter across. Now imagine the blueberry is an atom. If a single atom were the size of a blueberry, how big would the blueberry actually be? In other words, if we scaled everything up by the same factor needed to make an atom blueberry sized, what would happen to the blueberry itself? The answer is that the blueberry would be roughly the size of the Earth. Let me say that again. If you enlarged an atom to the size of a blueberry would become the size of the entire planet Earth. That's the scale we're dealing with. The ratio between an atom and a blueberry is roughly the same as the ratio between a blueberry and the Earth. This comparison works because an atom is approximately 1/10,000,000th of a meter across. A blueberry is about 1 centimeter or 1/100th of a meter, and the Earth is about 12,742 kilometers in diameter, or about 12,742,000 meters. The ratio between the blueberry and the atom is about 100 million. The ratio between Earth and the blueberry is roughly 1 billion. Those numbers aren't identical, but they're close enough in orders of magnitude that the comparison holds. The point is visceral, not mathematical. When you hold a blueberry and think about how impossibly small it is compared to the entire planet, that feeling of insignificance is roughly what an atom would feel like compared to that blueberry. So when you hold a blueberry, think about the relationship between that blueberry and the entire Earth. The blueberry is tiny compared to the planet, vanishingly small. If you placed a blueberry on a globe, you'd barely see it. Now take that same relationship, that same staggering difference in scale, and apply it in reverse. That's how small an atom is compared to the blueberry. The atom is to the blueberry what the blueberry is to the Earth. This means that the world you see around you, the room you're in right now, everything in it is built from objects so small that they bear the same relationship to a blueberry that a blueberry bears to the planet. Every surface, every object, every breath of air is composed of these almost inconceivably tiny building blocks, packed together in numbers so large that our language struggles to express them. Consider the air you're breathing right now. It seems like nothing. It's invisible. You can't feel individual molecules hitting your skin, and it seems like empty space between you and the walls. But every cubic centimeter of air at sea level contains about 25 billion molecules. That's 25 followed by 18 zeros, in a volume roughly the size of a sugar cube. Each one of those molecules, whether it's nitrogen, oxygen, argon, or carbon dioxide, is made of atoms. And each of those atoms is about 1/10,000,000th of a meter across. These molecules are moving incredibly fast. At room temperature, the average molecule of nitrogen in the air around you is traveling at about 500 meters per second. That's roughly 1,100 miles per hour. Faster than the speed of sound. Faster than a bullet from many firearms. These tiny molecules are crashing into your skin right now. Billions upon billions of them every fraction of a second. Collectively, they create what we call air pressure. The atmosphere pushes down on you with a force of about 10,000 kilograms per square meter. You don't feel it because you've lived with it your entire life. Your body is built to withstand it. But that pressure is nothing more than countless tiny atoms and molecules bouncing off you at incredible speeds. And not a single one of them is large enough for you to detect individually. Think about something as simple as smelling food cooking. When someone bakes bread, molecules from the bread drift through the air and eventually reach your nose. These molecules are tiny clusters of atoms. They travel through the air, bouncing off nitrogen and oxygen molecules millions of times along the way, until some of them happen to drift into your nostrils and land on receptors inside your nasal cavity. Those receptors detect the shape and chemistry of the molecules and send signals to your brain, which interprets them as the smell of bread. The entire experience of smell is really your brain detecting the arrival of individual molecules. But you need a certain number of those molecules to arrive before you notice anything. A single molecule of bread aroma landing on a receptor won't register. You need thousands or millions of them before the signal is strong enough for your brain to process. Atoms and molecules are so small that even your most sensitive biological systems need enormous numbers of them to produce a detectable signal. Here's another way to think about it. Imagine you had the ability to see individual atoms. Imagine your vision was somehow enhanced to perceive things at the atomic scale. What would the world look like? If you looked at a glass of water, you wouldn't see a smooth, clear liquid. You'd see an unimaginably vast swarm of tiny spheres packed together and jiggling frantically. Each sphere would be a water molecule, two small hydrogen atoms bonded to one larger oxygen atom. These molecules would be vibrating, rotating, sliding past each other in constant chaotic motion. The smooth surface of the water would reveal itself as a turbulent boundary where molecules are constantly escaping into the air and air molecules are constantly crashing into the surface. Nothing would be still. Everything at the atomic scale is in constant motion. Even in a solid block of ice, the atoms vibrate in place, trembling with thermal energy. The only way to stop this motion would be to cool the material to absolute zero, minus 273.15 degrees Celsius, a temperature that's impossible to reach in practice. If you looked at a metal surface, like a polished stainless steel countertop, you'd see atoms arranged in neat, crystalline patterns, layer upon layer of atoms stacked in regular geometric arrangements. But these layers wouldn't be perfectly smooth. There would be defects. Places where an atom is missing or where an extra atom has wedged itself into the wrong position. These defects might seem tiny, but they have enormous effects on the metal's properties. The strength, the flexibility, the corrosion resistance of a metal all depend on these atomic scale imperfections. Engineers who design bridges and aircraft and buildings are ultimately working with the consequences of how atoms arrange themselves. The scale of atoms affects everything. The color of the sky is determined by how light interacts with molecules of nitrogen and oxygen. The hardness of a diamond is determined by how carbon atoms are bonded together in a specific crystalline structure. The softness of graphite, which is also pure carbon, is determined by a different arrangement of the same carbon atoms. Same element, same atoms, but arranged differently, given completely different properties. Life itself is a consequence of atomic scale chemistry. The DNA in your cells is a long molecule made of atoms arranged in a specific sequence. That sequence encodes all the information needed to build and maintain your body. The information is stored in the order of molecular units called nucleotides, each made of about 30 to 35 atoms. Change a few atoms in the wrong place, and you change the protein that the DNA codes for. Change the protein, and you might change the function of a cell. Change the function of a cell, and you might change the organism. Evolution itself operates at the atomic scale, driven by mutations that alter the arrangement of atoms in DNA molecules. Every chemical reaction that happens in your body right now, the digestion of food, the transport of oxygen, the firing of neurons in your brain, all of it comes down to atoms interacting with other atoms, electrons being shared or transferred between atoms, bonds being formed and broken, energy being released or absorbed, your thoughts, your emotions, your memories. All of it is, at the deepest level, atoms doing what atoms do. And those atoms are so small that 10 million of them fit across a millimeter. So small that the atoms in a single drop of water rival the number of stars in the entire observable universe. So small that if you enlarged one to the size of a blueberry, the blueberry would become the size of the Earth. This is the scale we're dealing with. This is how small the building blocks of reality truly are. Everything you see, everything you touch, everything you are, is made of objects so tiny that humanity spent most of its existence not even knowing they existed. Objects so small that even our best optical instruments can't see them directly. Objects so numerous that the number of them in your own body is a 7 followed by 27 zeros. And we haven't even gotten inside the atom yet. Because as small as an atom is, the structures inside it are even smaller by orders of magnitude. The atom itself is almost entirely empty space. And what fills that space, what gives the atom its size and shape, is not at all what you might expect. The interior of the atom is one of the strangest places in the known universe. It's a place where the rules of everyday physics break down completely, where objects don't have definite positions, where things could be in two places at once, where the very act of measuring something changes what you're measuring. But to understand all of that, we first need to go inside. We need to shrink down from the scale of the atom to the scale of the nucleus. And that journey, as short as it sounds, covers one of the most astonishing differences in scale anywhere in nature. Now that we have some sense of how small an atom is from the outside, let's go inside one. Because what you find inside an atom is in many ways even more astonishing than how small the atom itself is. The interior of an atom is one of the most counterintuitive places in all of nature. It's a place that defies everything your everyday experience has taught you about how the world works. And the single most shocking thing about the inside of an atom is this: there's almost nothing there. An atom is overwhelmingly, staggeringly, almost entirely empty space. The amount of actual matter inside an atom, the stuff that has mass, the stuff that weighs something, occupies such a tiny fraction of the atom's total volume that it's difficult to express in words. We're not talking about an atom being half empty or 90% empty. We're talking about an atom being more than 99.99999999999% empty. The amount of matter in an atom compared to the space it occupies is so vanishingly small that the atom might as well be nothing at all. And yet, that tiny speck of matter is what gives the atom its mass, its identity, its place on the periodic table. Everything that makes an atom what it is, everything that determines whether it's hydrogen or gold or oxygen, is packed into a space so small that the rest of the atom is essentially a void. Let's break this down carefully. An atom has two main components. At the center is the nucleus. This is where essentially all of the atom's mass is concentrated. The nucleus is made of protons and neutrons, particles that are bound together by an incredibly powerful force called the strong nuclear force. Surrounding the nucleus, at a relatively enormous distance, is the electron cloud. This is where the electrons exist. Electrons are tiny particles with very little mass that carry a negative electrical charge. They're attracted to the positively charged protons in the nucleus by the electromagnetic force, and this attraction is what holds the atom together. Now here's where the scale gets truly wild. The nucleus of a typical atom is about 1 femtometer across. A femtometer is 1 quadrillionth of a meter. That's 1/1,000,000th of a nanometer. The atom itself, defined by the outermost boundary of the electron cloud, is about 1/10th of a nanometer across, or 100,000 femtometers. This means the atom is roughly 100,000 times larger than its nucleus. 100,000 times. That ratio is the key to understanding everything about what makes atoms so astonishingly empty. Because when you say something is 100,000 times smaller in diameter, the difference in volume is far more extreme. Volume scales with the cube of the diameter. If the nucleus is 100,000 times smaller across, then the volume of the nucleus compared to the volume of the atom is 100,000 cubed, which is 1 followed by 15 zeros. 1 quadrillion. The nucleus occupies roughly 1 quadrillionth of the atom's volume. That's the fraction of the atom that contains actual matter. The rest, the other 999 trillion, 999 billion, 999 million, 999,000, 999 parts out of a quadrillion, is empty. Not empty in the way a room is empty when there's no furniture. Not empty in the way space between planets is empty. Empty in a way that's hard to even define because there's nothing there to define. No substance, no material, nothing you could touch or hold or weigh. Just space. Just distance between the nucleus and the electrons. Let's try to visualize this, because numbers like 100,000 to 1 can be hard to process. The most famous comparison, and it's famous because it works so well, uses a football stadium. Imagine a large football stadium, a professional one, the kind that seats 70 or 80,000 people. The field, the stands, the upper decks, the roof if it has one. Picture the whole thing. Now imagine that this entire stadium represents a single atom. The atom fills the stadium from edge to edge, floor to ceiling. Now ask yourself, where's the nucleus? The nucleus, which contains over 99.9% of the atom's mass, would be a small marble sitting at the center of the 50-yard line. A marble in an entire stadium. That's the relationship between the nucleus and the atom. The marble is the nucleus, the stadium is the atom, and everything between the marble and the walls of the stadium is empty space. There's nothing there. No matter, no substance. Just the vast emptiness between the nucleus and the outermost reach of the electron cloud. And the electrons? They'd be even smaller than the marble. Far smaller. Electrons are so tiny that if we're representing the nucleus as a marble, the electrons would be essentially invisible. You'd need a powerful magnifying glass just to see them, and they'd be somewhere out in the stands or up near the roof, impossibly far from the marble at the center. The stadium comparison gives you a feel for it, but it actually undersells the emptiness. A real stadium has seats, has concrete, has steel beams. It's filled with stuff. The inside of an atom has none of that. It's just space. Let me try another comparison. Imagine you scaled up a hydrogen atom so that the nucleus, which in this case is a single proton, was the size of a basketball. A regular basketball, about 24 centimeters across. If the proton were the size of a basketball, how big would the atom be? The atom, defined by the average distance of the single electron from the nucleus, would be about 12 kilometers across. 12 kilometers. That's roughly 7.5 miles. The basketball would be sitting at the center, and the electron would be somewhere near the edge of that 12-kilometer sphere. Everything in between would be empty. Completely empty. You could walk from the basketball toward the edge of the atom and walk for miles through absolute nothingness. No matter, no particles, nothing to interact with. Just vacant space. Or try this one. Imagine you could blow up a single atom to the size of the dome of St. Peter's Basilica in Vatican City, one of the largest domes in the world. The dome has an internal diameter of about 42 meters. If the atom were the size of that dome, the nucleus would be smaller than a grain of sand sitting at the very center of the floor beneath the dome. The entire soaring structure, all that space above and around you, would represent the empty interior of a single atom. And at the center, barely visible on the ground, would be a speck containing almost all of the atom's mass. Here's one more. Imagine you expanded a single atom to the size of Earth. Earth has a diameter of about 12,742 kilometers. If the atom were the size of the entire planet, the nucleus would be a sphere roughly 127 meters across, about the length of a football field and a quarter. That's it. A football field-sized ball at the center of the entire Earth. The rest of the planet, from the core to the surface to the atmosphere, would be empty space. Mountains, oceans, continents, all of it in this analogy would just be void. Nothing. And that football field-sized sphere at the center would contain more than 99.9% of all the mass. Everything else, the electrons occupying that vast atomic volume, would contribute almost nothing to the total weight. Let me be more precise about the mass distribution because it's important. The nucleus doesn't just contain most of the mass, it contains almost all of it. A proton has a mass of about 1.67 times 10 to the negative 27 kilograms. An electron has a mass of about 9.11 times 10 to the negative 31 kilograms. That means a proton is about 1,836 times more massive than an electron. A neutron is very slightly heavier than a proton, about 1,839 times the mass of an electron. In a carbon atom, for example, you have 6 protons, 6 neutrons, and 6 electrons. The 6 protons and 6 neutrons make up the nucleus. The 6 electrons form the cloud. The combined mass of the 6 electrons is about 3,700 times less than the combined mass of the 12 nuclear particles. The electrons contribute roughly 0.03% of the atom's total mass. The nucleus gets the other 99.97%. So when you pick up a rock or hold a glass of water or lift your own body out of bed in the morning, the weight you feel, the mass that gravity is pulling on, is almost entirely concentrated in the nuclei of atoms. Those tiny, almost incomprehensibly small specks at the centers of atoms are where virtually all the mass in your body resides. The electrons, which define the atom's size and determine its chemical behavior, contribute almost nothing to the weight. You are, in a very real sense, a collection of atomic nuclei separated by vast stretches of empty space and held in formation by clouds of nearly massless electrons. This leads to one of the most striking thought experiments in physics. What would happen if you could remove all the empty space from the atoms in your body? What if you could compress all the nuclear matter, all the protons and neutrons, down until they were touching, packed together with no gaps? How small would you be? The answer is almost too small to believe. If you removed all the empty space from the atoms in a human body, the remaining matter, all the protons and neutrons packed together at nuclear density, would fit in a cube roughly 1/100th of a millimeter on each side. That's smaller than a grain of sand, much smaller. It's about the size of a very small speck of dust, barely visible to the naked eye. All of you. Every bone, every muscle, every organ, every drop of blood, every thought encoded in your neural connections, compressed into a space smaller than a grain of fine dust. And it would be incredibly heavy. It would still have your full mass, or 60 or 70 or 80 kilograms, packed into that tiny volume. The density would be absurd. We're talking about the density of nuclear matter, roughly 230 billion kilograms per cubic centimeter. A teaspoon of this material would weigh about 1.15 trillion kilograms. That's more than the weight of a small mountain compressed into a space you could hold between your fingers, if you somehow could hold it, which you couldn't, because the gravitational force of that concentrated mass would be significant. This isn't just a thought experiment. This kind of matter actually exists. Neutron stars are astronomical objects where gravity has crushed matter to nuclear density. When a massive star dies in a supernova explosion, its core can collapse under its own gravity. If the core is massive enough, the protons and electrons are crushed together, forming neutrons. The entire core becomes a giant ball of nuclear matter. A typical neutron star is only about 20 kilometers across, smaller than most cities, but it contains 1 to 2 times the mass of our entire sun. A teaspoon of neutron. Star material would weigh about 6 billion tons on Earth. That's the density you'd get if you removed all the empty space from atoms and packed the nuclear matter together. And it exists. It's real. There are neutron stars throughout our galaxy, each one a testament to how much empty space normally separates the nuclei in ordinary matter. Let me expand the compression thought experiment even further, because it really drives home how empty matter is. If you removed all the empty space from the atoms of every human being on Earth, all 8 billion of us, the remaining nuclear matter would fit in a volume roughly the size of a sugar cube. 8 billion people. Every person who has ever argued about anything, every athlete, every politician, every artist, every scientist, every baby, every grandparent. Compress them all down and you get a sugar cube. A very heavy sugar cube, admittedly. It would weigh about 480 billion kilograms, roughly the mass of a small asteroid, but physically, it would fit on a teaspoon. This is because atoms are that empty. The matter in 8 billion human bodies, when you strip away the empty space, fits in your hand. Now let's think about what this means for the world around you. Look at the floor beneath your feet. It seems solid. It seems like a continuous, unbroken surface. but it's made of atoms, and those atoms are mostly empty space. The concrete or wood or tile is overwhelmingly nothing. The table in front of you, if there is one, is overwhelmingly nothing. The walls around you are overwhelmingly nothing. Your own body is overwhelmingly nothing. If you could somehow see at the atomic scale, you wouldn't see solid objects. You'd see vast gulfs of emptiness dotted with incredibly tiny points of nuclear matter, surrounded by faint clouds of electrons. The appearance of solidity is, in a sense, an illusion. A very convincing illusion created by the forces between atoms rather than by the presence of actual material filling space. It's important to be clear about what we mean when we say the atom's size versus the nucleus's size, because these are two very different things, and confusing them leads to misunderstanding. The size of an atom is defined by its electron cloud. The electrons don't orbit at a single fixed distance. They exist in a fuzzy region around the nucleus, and the boundary of that region is what we call the size of the atom. Different atoms have different sizes because they have different numbers of electrons arranged in different configurations. A hydrogen atom, the simplest atom with just one proton and one electron, has a diameter of about 1.06 angstroms, roughly 106 picometers. A cesium atom, which has 55 protons, 55 electrons, and typically 78 neutrons, is much larger, about 5.2 angstroms across. The electron cloud extends farther from the nucleus because there are more electrons occupying higher energy levels. The nucleus, on the other hand, is determined by the number of protons and neutrons it contains. A hydrogen nucleus is just a single proton, about 1.7 femtometers across. A uranium nucleus, with 92 protons and 146 neutrons, is about 15 femtometers across. Larger, yes, but still incredibly tiny compared to the atom. Even the largest nuclei are more than 10,000 times smaller than the smallest atoms. This distinction matters because when people talk about the size of an atom, they sometimes confuse it with the size of the nucleus. But these are dramatically different scales. The atom is defined by its electrons. The nucleus is a tiny core buried deep inside. And the space between them, the space that makes up the overwhelming majority of the atom's volume, is genuinely empty. There's nothing there. No miniature structures, no hidden particles, no invisible scaffolding. Just the quantum mechanical probability of finding an electron at various distances from the nucleus. This emptiness was one of the most surprising discoveries in the history of science. In the early 1900s, scientists were just beginning to figure out the internal structure of atoms. The dominant model at the time was J.J. Thomson's plum pudding model, proposed in 1904. Thomson, who had discovered the electron in 1897, imagined the atom as a sphere of positive charge with electrons embedded in it like raisins in a pudding. In this model, the positive charge was spread uniformly throughout the atom. There was no nucleus. The atom was a solid ball of charge with electrons scattered inside it. This model made intuitive sense. Matter feels solid, so atoms should be solid. The positive and negative charges should be mixed together, filling the atomic volume. There was no reason to suspect that the atom had a tiny, dense core surrounded by empty space. No everyday experience would suggest such a thing. But in 1909, Ernest Rutherford, working at the University of Manchester, designed an experiment that would overturn this picture entirely. The experiment is one of the most famous in the history of physics, and it's famous because the result was so completely unexpected. Rutherford directed his colleagues Hans Geiger and Ernest Marsden to fire alpha particles at a thin sheet of gold foil. Alpha particles are helium nuclei, 2 protons and 2 neutrons bound together. They're small and fast, moving at about 5% of the speed of light in these experiments. The gold foil was extremely thin, only about 400 nanometers thick, which was just a few thousand atoms across. If Thomson's plum pudding model was correct, the alpha particles should have passed through the foil with only minor deflections. The positive charge in the gold atoms would be spread throughout each atom, so the alpha particles would encounter only a diffuse, weak electric field as they pass through. They might be nudged slightly off course, but nothing dramatic should happen. And for the vast majority of alpha particles, that's exactly what happened. Most of them sailed straight through the gold foil as if it wasn't there. This was expected, but then something strange showed up in the data. A small fraction of the alpha particles were deflected at large angles. Some bounced back at angles greater than 90 degrees. A few came almost straight back toward the source, as if they had hit something solid and bounced off it. Rutherford was stunned. He later described the result using what has become one of the most quoted lines in physics. He said it was as if you fired a 15-inch artillery shell at a sheet of tissue paper, and the shell came back and hit you. It made no sense under the plum pudding model. If the positive charge was spread evenly throughout the atom, nothing in the foil could produce such a strong deflection. The alpha particles were moving too fast and the diffuse charge was too weak. Something else was going on. The only explanation was that the positive charge in the gold atoms was not spread throughout the atom. It was concentrated in a tiny, incredibly dense region at the center. When an alpha particle happened to pass close to this concentrated charge, the electromagnetic repulsion was so intense that it could deflect the particle through large angles or even send it straight back. But because this region of concentrated charge was so small, the overwhelming majority of alpha particles never came anywhere near it. They sailed through the vast empty space of the atom without encountering anything significant. Rutherford published his analysis in 1911. He proposed that the atom consisted of a tiny, dense, positively charged nucleus surrounded by orbiting electrons. The nucleus was where essentially all the mass was located. The electrons occupied the rest of the atomic volume, but that volume was mostly empty. Space. This was a completely new picture of the atom. It replaced the solid, filled-in atom of Thomson's model with something that was almost entirely nothing. The atom went from being a solid ball to being a vast empty space with a speck of matter at its center. And Rutherford's evidence was compelling. The scattering pattern of the alpha particles matched his mathematical predictions almost perfectly. The data demanded a tiny, dense nucleus. Think about what Rutherford's experiment revealed. When you fire particles of gold foil, most of them pass straight through. The foil is made of atoms, and the atoms are overwhelmingly empty. The particles fly through the empty space inside the atoms as if the foil were barely there. Only the rare particle that happens to approach close to a nucleus gets deflected. The atoms in the foil are like stadium after stadium after stadium, each with a marble at the center. Fire a bullet through thousands of empty stadiums and it will almost certainly pass through without hitting any of the marbles. But once in a great while, a bullet will pass close enough to a marble to be deflected. The Rutherford experiment changed everything. It established the nuclear model of the atom, which is still the foundation of our understanding today. The atom is mostly empty space. The mass is concentrated in the nucleus. The electrons define the atom's size but contribute almost nothing to its mass. This picture has been refined enormously over the past century. We now know that protons and neutrons are themselves made of quarks. We understand the forces that hold the nucleus together. We have detailed mathematical descriptions of electron behavior. But the basic picture that Rutherford established in 1911, the atom as a tiny dense nucleus surrounded by a vast cloud of electrons, that picture remains fundamentally correct. And that picture is deeply strange, because it means the matter you interact with every day, the solid objects, the liquids, the gases, all of it is made of atoms that are overwhelmingly nothing. The chair you're sitting in is mostly empty space. The ground beneath you is mostly empty space. You are mostly empty space. The appearance of solidity, the feeling that objects are continuous and filled and substantial is not because atoms are packed tightly together with no gaps. Atoms are packed together, yes, but each atom is itself a vast emptiness with a speck of matter at its heart. The solidity you experience comes from something else entirely, something we'll get to later, but for now, sit with this idea. The world is not what it seems. The solid, substantial reality you've lived in your entire life is built from building blocks that are almost entirely empty. The floor supports your weight, the walls contain the room, the glass holds your water. All of this is happening despite the fact that the atoms involved are more than 99.99999999999% empty space. The universe figured out a way to build everything you've ever seen, touched, or experienced from almost nothing at all. And inside each of those atoms, the electrons that define the atom's size and shape behave in ways that would seem impossible based on your everyday experience. They don't orbit the nucleus like planets around a sun, despite what you may have been taught. They do something far stranger, far more beautiful, and far more fundamental. And understanding what they actually do is the key to understanding why atoms work the way they do. If you went to school anywhere in the world and learned anything about atoms, you were almost certainly shown a picture that looks something like this. A small cluster of spheres at the center representing protons and neutrons, and around that cluster, little balls following circular or elliptical paths, like planets orbiting a sun. The little balls were labeled electrons. The orbits were drawn as clean, crisp lines. Maybe some orbits were closer to the nucleus and some were farther out. Maybe the electrons were color-coded. The picture was neat, tidy, and easy to understand. It made the atom look like a miniature solar system. The nucleus was the sun. The electrons were the planets. Gravity was replaced by electromagnetic attraction, but otherwise the structure was the same. Neat, organized, predictable. And this picture is wrong, not a little bit wrong, not approximately right with minor corrections needed. It's fundamentally, deeply, conceptually wrong. It's wrong in a way that misrepresents the nature of reality at the atomic scale. Electrons do not orbit the nucleus like tiny planets. They don't follow defined paths. They don't trace neat circles or ellipses around a central point. What electrons actually do is so different from this picture that it required an entirely new branch of physics to describe. A branch so strange, so counterintuitive, so far removed from everyday experience that even the physicists who developed it struggled to accept what was telling them about reality. But before we get to what electrons actually do, let's understand why the planetary model seemed reasonable in the first place, and why it ultimately failed. Because the story of how we figured out what electrons are really doing is one of the greatest intellectual journeys in human history. It's a story about people looking at the evidence, finding that it contradicted everything they thought they knew, and being forced to accept a reality that defied common sense. After Rutherford discovered the nucleus in 1911, the obvious next question was, how did the electrons arrange themselves around it? Rutherford's own model simply placed electrons orbiting the nucleus like planets around a star. This was intuitive. We understood planetary orbits. Newton's laws of gravity described them beautifully. If you replaced gravitational attraction with the electromagnetic attraction, you could apply similar mathematics. The electron would orbit the nucleus at a specific distance, held in place by the balance between its forward momentum and the inward pull of the electromagnetic force, just like Earth is held in its orbit by the balance between its motion and the sun's gravity. The math worked. Superficially, you could calculate orbits and get numbers that seemed reasonable. But there was an immediate, devastating problem. According to classical electromagnetism, the physics that described electricity and magnetism as understood in the late 1800s, a charged particle moving in a curved path must radiate energy. This was well established. When you accelerate a charged particle, it emits electromagnetic radiation. An electron orbiting a nucleus is constantly accelerating because it's constantly changing direction. It's moving in a circle, and circular motion is acceleration, even if the speed doesn't change, because the direction is always changing. So, classical physics predicted that an orbiting electron should continuously emit electromagnetic radiation and lose energy. As it loses energy, it should spiral inward toward the nucleus, emitting radiation at higher and higher frequencies as it spirals closer and closer. This process should happen incredibly fast. Calculations showed that a classical orbiting electron would spiral into the nucleus in roughly 16 trillionths of a second. That's about 100th of a billionth of a second. In other words, atoms shouldn't be stable. They should collapse almost instantly. Every atom in the universe should have self-destructed within a tiny fraction of a second of forming. Obviously, this doesn't happen. Atoms are remarkably stable. The hydrogen atoms in a glass of water are the same hydrogen atoms that formed in the first few minutes after the Big Bang, 13.8 billion years ago. They haven't collapsed. They haven't decayed. They've been perfectly stable for almost the entire history of the universe. The planetary model predicted instant collapse, and reality showed perfect stability. Something was deeply wrong with the model. In 1913, the Danish physicist Niels Bohr proposed a modification that patched the problem, at least temporarily. Bohr suggested that electrons could only orbit the nucleus at specific quantized distances. Not any orbit would do. Only certain special orbits were allowed. While in these allowed orbits, the electron would not radiate energy, even though classical physics said it should. The electron could jump from one allowed orbit to another by absorbing or emitting a precise amount of energy, but it couldn't exist between the allowed orbits. This was a bold idea. Bohr was essentially saying that the rules of classical physics didn't apply at the atomic scale. He offered no deep explanation for why only certain orbits were allowed. He simply imposed the rule because it worked. And it worked brilliantly for hydrogen. Bohr's model correctly predicted the wavelengths of light emitted by hydrogen atoms. When hydrogen gas is heated or subjected to an electrical discharge, it glows with specific colors. Not a continuous rainbow of light, but distinct sharp lines, at very specific wavelengths. These spectral lines had been measured with extraordinary precision, and nobody could explain their pattern. Bohr's model predicted those exact wavelengths. It was a triumph. For the first time, someone had a mathematical model that could predict the behavior of an atom. But Bohr's model had serious limitations. It worked well for hydrogen, which has only one electron. When scientists tried to apply it to more complex atoms with multiple electrons, the predictions started to fail. The model couldn't accurately predict the spectra of helium or lithium or any element beyond hydrogen. It also couldn't explain why only certain orbits were allowed. The rule was imposed by hand without any deeper justification. And the picture it created, electrons moving in fixed circular orbits at specific distances from the nucleus, was still essentially classical. It was still imagining the electron as a tiny ball moving along a defined path. It just restricted which paths were permitted. Something more radical was needed. And in the 1920s, that radical revolution arrived. It came from several brilliant minds working in parallel, approaching the problem from different angles, and arriving at a picture of reality so strange that it shook the foundations of physics. In 1924, a French physicist named Louis de Broglie proposed something extraordinary. He suggested that electrons, which everyone had assumed were particles, tiny balls of matter with a definite position and velocity, also behaved as waves. This wasn't a metaphor. De Broglie proposed that every particle has a wavelength associated with it, and that wavelength is inversely proportional to the particle's momentum. A heavier, faster particle has a shorter wavelength. A lighter, slower particle has a longer wavelength. For everyday objects like baseballs and cars, the wavelength is so incomprehensibly tiny that it's completely undetectable. But for something as small and light as an electron, the wavelength is significant. It's comparable to the size of an atom. De Broglie's idea explained Bohr's quantization rule beautifully. If electrons behave as waves, then only certain orbits are allowed, because only certain orbits allow the electron wave to fit perfectly around the nucleus. Like a standing wave on a guitar string, the wave has to close on itself smoothly. If the orbit's circumference isn't a whole number of wavelengths, the wave interferes with itself destructively, and that orbit is forbidden. Only orbits where the electron wave fits exactly are stable. The quantization that Bohr had imposed by hand now had a natural explanation. But de Broglie's insight was just the beginning. Past 1925 and 1926, the revolution accelerated. Werner Heisenberg, a young German physicist, developed a mathematical framework called matrix mechanics that described atomic behavior using abstract mathematical objects. Independently, Erwin Schrödinger, an Austrian physicist, developed a different mathematical framework called wave mechanics. Schrödinger's approach was built around a mathematical object called the wave function, usually represented by the Greek letter psi. The wave function describes the state of a quantum system, like an electron in an atom. It's a mathematical function that assigns a complex number to every point in space. And its physical meaning is this: the square of the wave function at any point in space gives the probability of finding the electron at that point. Not the certainty, the probability. This was the key insight, and it was deeply disturbing to many physicists. The wave function doesn't tell you where the electron is. It tells you where the electron might be. Before you measure the electron's position, it doesn't have a definite position. It exists in a superposition of all possible positions simultaneously, with the probability of each position given by the wave function. When you actually measure the position, the wave function collapses and you find the electron at one specific location. But before the measurement, asking where the electron is has no answer. The electron is not anywhere specific. It's everywhere at once, with different probabilities. This is not a limitation of our instruments. This is not because our measuring devices aren't good enough and the electron is really at a specific spot we just can't pinpoint. Quantum mechanics says this uncertainty is fundamental. It's built into the fabric of reality. The electron genuinely does not have a definite position until it's measured. This isn't about what we know, it's about what exists. The electron's position before measurement isn't hidden. It's undefined. Werner Heisenberg formalized this idea in 1927 with his famous uncertainty principle. The uncertainty principle states that you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you know one, the less precisely you can know the other. This isn't about measurement error. It's not that your instruments are shaking or your equipment is imprecise. It's a fundamental limit imposed by nature itself. If you measure an electron's position with perfect precision, you know exactly where it is at that instant. But at that same instant, its momentum becomes completely undefined. You have no idea how fast it's moving or in what direction. Conversely, if you measure its momentum with perfect precision, you know exactly how fast it's moving and in what direction. But now its position becomes completely undefined. It could be anywhere. Think about what this means for the idea of an orbit. An orbit is a path, a trajectory. To describe an orbit, you need to know the object's position and momentum at every point in time. Where is it, and how fast is it moving in what direction? But the uncertainty principle says you can never know both of these simultaneously. So you can never describe an electron's orbit, not because you lack the technology, but because the orbit doesn't exist. The electron doesn't follow a path. It doesn't trace a trajectory. The very concept of a trajectory is meaningless for an electron in an atom. This is why the planetary model is so deeply wrong. Not because it gets the details wrong, but because the entire framework it's built on, the idea of a particle following a defined path, doesn't apply at the atomic scale. It's like trying to describe the color of a sound. The concepts don't match. Electrons and orbits don't go together. So if electrons don't orbit the nucleus, what do? The answer is that they exist as probability clouds. The wave function describes a region of space around the nucleus where the electron is likely to be found. This region is called an orbital. Not an orbit, an orbital. The difference in that one syllable represents one of the most profound shifts in the history of human thought. An orbit is a path, an orbital is a shape, a probability distribution, a map of where the electron is most likely to be found if you looked for it. The simplest orbital is called the 1s orbital. This is the ground state of hydrogen, the lowest energy state of the simplest atom. The 1s orbital is spherical. It's a fuzzy sphere centered on the nucleus, densest near the center and fading gradually with distance. There's no sharp boundary. The probability of finding the electron decreases smoothly as you move away from the nucleus, but it never quite reaches zero. Technically, there's a tiny, incredibly small probability of finding the electron miles away from the nucleus. In practice, we draw the boundary of the orbital where the probability drops below some threshold, capturing 90 or 95% of the probability inside the boundary. The most probable distance for an electron in a hydrogen 1s orbital is about 53 picometers from the nucleus. This is called the Bohr radius, named after Niels Bohr because it matches the radius of the innermost orbit in his model. But unlike Bohr's orbit, where the electron was always exactly at this distance, in the real atom, the electron could be closer or farther. 53 picometers is just the most likely distance. Sometimes the electron is found closer to the nucleus, sometimes farther away. The probability cloud extends in all directions, fading with distance but never quite disappearing. As you go to higher energy levels, the orbitals get more complex and more interesting. The 2s orbital is also spherical but larger, and it has a node, a region where the probability of finding the electron drops to 0, separating an inner sphere from an outer sphere. The 3s orbital has 2 nodes, creating 3 concentric spheres. Each successive s orbital is larger and has more nodes, like nested Russian dolls made of probability. But the really strange shapes appear with the p orbitals. These aren't spheres, they're dumbbell-shaped, like 2 teardrops pointing in opposite directions from the nucleus. There are 3 p orbitals at each energy level, oriented along the 3 spatial axes. They look like a 3-dimensional cross, with each dumbbell pointing in a different direction. The electron in a p orbital is most likely to be found in one of the 2 lobes of the dumbbell. There's a node at the nucleus itself, the center of the dumbbell, where the probability of finding the electron is exactly 0. The electron exists in the lobes on either side of the nucleus, but never at the nucleus itself. The d orbitals, which become available at the 3rd energy level and above, are even more exotic. Most d orbitals have 4 lobes, arranged in a clover leaf pattern. One of the 5 d orbitals looks like a dumbbell with a ring around its middle. These shapes aren't arbitrary. They're precise mathematical solutions to Schrödinger's equation for the hydrogen atom. They emerge naturally from the mathematics of quantum mechanics. Nobody designed them, nobody chose them. They're what the equations produce when you solve them correctly. And then there are f orbitals, which become available at the 4th energy level. These have even more complex shapes with multiple lobes pointing in various directions. The patterns become increasingly intricate as you move to higher energy levels, but they always follow the mathematics of the wave equation. The shapes of these orbitals determine the chemical behavior of atoms. Why does carbon form 4 bonds? Because of the shapes of its orbitals. Why does oxygen tend to form 2 bonds? Because of the shapes of its orbitals. Why do transition metals have such varied chemistry? Because their d orbitals provide multiple ways to share electrons. The entire periodic table, all the chemical properties of every element, all the reactions that make life possible, all of it flows from the shapes of electron orbitals. And those shapes come from quantum mechanics, from the wave function, from the probability distributions that describe where electrons are likely to be found. Here's something that really drives home how different quantum reality is from everyday experience. In the classical picture, if you have an electron in a particular orbit, it's always somewhere on that orbit. You might not know where it is on the orbit at any given moment, but you know it's on the orbit somewhere, moving along its path. In the quantum picture, the electron simply doesn't have a path. Between measurements, it doesn't have a position at all. It's not that the electron is at some specific location and we just don't know where. The electron genuinely doesn't have a specific location. It exists as a probability cloud spread out across space, with the wave function determining how that probability is distributed. This is what bothered an Einstein so profoundly. Einstein accepted the mathematics of quantum mechanics. He acknowledged that the predictions were correct, but he couldn't accept that the theory was telling us something fundamental about reality. He believed that the electron must have a definite position at all times, and that quantum mechanics was simply an incomplete description that failed to capture the full picture. He famously said that God does not play dice, expressing his discomfort with the inherent randomness of quantum mechanics. Bohr reportedly replied that Einstein should stop telling God what to do. This debate between Einstein and Bohr lasted for decades, and drove some of the deepest thinking about the nature of reality in the 20th century. Einstein devised increasingly clever thought experiments, trying to show that quantum mechanics was incomplete. Bohr and others found ways to refute each one. In the end, experiments have consistently sided with quantum mechanics. The uncertainty is real. The randomness is genuine. Nature at the atomic scale is fundamentally probabilistic. In 1964, the physicist John Bell proposed a theorem that could distinguish between quantum mechanics and any theory that gave electrons definite positions at all times, the kind of theory Einstein preferred. Bell's theorem showed that these two types of theories make different predictions for certain carefully designed experiments. In the decades since, numerous experiments have tested Bell's theorem. The results have consistently confirmed quantum mechanics and ruled out the kind of hidden variable theories Einstein hoped for. Most dramatically, in 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for their experimental work confirming violations of Bell's inequalities. Their experiments demonstrated conclusively that quantum entanglement is real and that particles do not have definite properties before measurement. Nature is genuinely random at the quantum level. This isn't a gap in our knowledge, it's a feature of reality. So the electron in an atom is not a tiny planet orbiting a nucleus. It's a quantum entity described by a wave function, existing as a probability cloud, without a definite position until measured. It occupies an orbital, a three-dimensional shape determined by quantum mechanics, and the shape of that orbital determines the atom's chemical properties. The neat, clean picture of electrons circling the nucleus like planets around the sun is a useful simplification for introduction, but it's not what's actually happening. What's actually happening is far stranger and far more beautiful. Let me try one more way to convey this. Imagine you had a magical camera that could photograph a single electron in a hydrogen atom. You point at the atom and snap a picture. You see a tiny dot somewhere near the nucleus. That's where the electron was at the instant you took the photo. Now you reset the atom to the same state and take another photo. The dot appears somewhere else. Reset photo, different position. Reset photo, different position again. After millions of photographs, you notice a pattern. The dots aren't random. They cluster near the nucleus and become sparser farther away. If you overlay all the photos, the dots form a spherical cloud, densest near the center and fading with distance. That cloud is the 1s orbital. It's the probability distribution made visible through millions of individual measurements. No single measurement tells you where the electron is in any predictable way. Each measurement gives a different answer, but the statistical pattern across many measurements is perfectly predictable. Quantum mechanics doesn't tell you what will happen in any single measurement. It tells you what will happen on average across many measurements, and its predictions for those averages are the most accurate in all of science. This quantum behavior isn't limited to electrons in atoms. It's a fundamental feature of nature at small scales. Protons behave quantum mechanically. Neutrons behave quantum mechanically. Even whole atoms and small molecules exhibit quantum behavior under the right conditions. Physicists have demonstrated quantum interference with molecules containing over 2,000 atoms. The larger the object, the harder it is to observe quantum effects because interactions with the environment cause the quantum behavior to decohere, essentially washing out the wave-like properties. But the quantum nature is always there, underlying everything. For the atoms that make up your body, quantum mechanics is operating at every moment. The electrons in every atom, in every molecule, in every cell are existing as probability clouds right now. The chemical bonds holding your DNA together are quantum mechanical. The way your enzymes catalyze reactions is quantum mechanical. The way your neurons fire involves quantum tunneling of protons and electrons across energy barriers. You are quite literally a quantum mechanical object. The fact that you don't notice quantum effects in your daily life is because you're made of so many atoms that the individual quantum fluctuations average out. The classical world you experience is the statistical average of an unimaginably vast number of quantum events happening simultaneously. This is one of the deepest insights of modern physics. The solid, predictable, deterministic world we experience is emergent. It arises from an underlying reality that is fundamentally probabilistic and uncertain. The atoms that make up your world are governed by rules that would seem absurd if you encountered them directly. Particles that don't have positions until measured. Waves that are also particles. Entities that can tunnel through barriers they shouldn't be able to cross. But when you combine trillions upon trillions of these quantum objects, their collective behavior averages out into the smooth, predictable, solid-seeming world you know. And this brings us to perhaps the deepest question about atoms, and the one we have to tackle directly. If atoms are mostly empty space, and if the electrons in atoms don't even have definite positions, existing instead as fuzzy probability clouds, then why does anything feel solid? Why can you stand on the ground without falling through it? Why can't you push your hand through a table? Why does a wall stop you? If atoms are overwhelmingly nothing, if the matter inside them occupies less than a trillionth of their volume, why doesn't everything just pass through everything else? The answer is not what most people expect. It's not about atoms being like solid billiard balls that stack together to create solid objects. It's about forces, invisible, powerful forces that operate across the empty space inside atoms and between atoms, creating the illusion of solidity in a world built from almost nothing at all. You're sitting somewhere right now, maybe on a chair, maybe on a couch, maybe lying in bed. Whatever surface is supporting you, it feels solid. Completely, undeniably solid. Your weight presses down and the surface pushes back. There's no ambiguity. There's no give beyond what you'd expect from the material. The chair doesn't let you sink through it. The floor beneath the chair doesn't let the chair sink through it. The ground beneath the floor doesn't let any of it sink through. Everything holds. Everything supports. Everything feels firm and real and substantial. And now you know that every atom in that chair, every atom in the floor, every atom in your body is more than 99.99999999999% empty space. The nuclei in those atoms occupy a trillionth of the atomic volume. The electrons are probability clouds without definite positions. The whole structure, from your body to the chair to the floor to the ground, is built from objects that are overwhelmingly nothing. So why doesn't everything just pass through everything else? Why can't you fall through your chair the way Rutherford's alpha particles sail through gold foil? Why does the world feel solid when it's built from emptiness? This is one of the most important questions you can ask about the physical world. And the answer reveals something profound about the nature of reality. The solidity you feel every day, the resistance of surfaces, the firmness of objects, the feeling of contact between your body and the world around you, none of it is caused by matter touching matter. None of it is caused by solid things pressing against other solid things. The sensation of solidity is created entirely by forces. Invisible, powerful forces acting across the empty space inside and between atoms. You have never, in your entire life, touched anything. Not really. Not in the way you think. Every sensation of contact you've ever experienced has been the result of electromagnetic forces pushing back against you from a distance. The atoms in your fingertip have never made physical contact with the atoms in anything you've ever held. They've come close, incredibly close by everyday standards, but at the atomic scale, there's always a gap, always a distance, always empty space between your atoms and the atoms of whatever you think you're touching. And across that gap, forces are doing all the work. Let me explain how this works. When two atoms approach each other, their electron clouds begin to interact. Remember, the electron cloud defines the size of the atom. It's the fuzzy boundary where electrons are likely to be found. When the electron clouds of two atoms get close enough, the negatively charged electrons in one cloud start to repel the negatively charged electrons in the other cloud. Like, charges repel each other. This is the electromagnetic force, one of the four fundamental forces of nature, and it's extraordinarily powerful at atomic scales. As the atoms get closer, this repulsion increases rapidly. It's not a gentle pushback. It's an aggressive, escalating resistance that grows stronger and stronger the closer the atoms get. The force follows an inverse relationship with distance, meaning that halving the distance dramatically increases the repulsion. Trying to push two atoms closer together once their electron clouds overlap is like trying to push two incredibly powerful magnets together with the same poles facing each other. The closer you push, the harder they push back. This electromagnetic repulsion is what you feel when you press your hand against a table. The electron clouds in the atoms of your skin are being repelled by the electron clouds in the atoms of the table's surface. Your hand slows down, stops, and you feel resistance. That resistance isn't matter hitting matter. It's electromagnetic force fields interacting across empty space. The atoms in your hand never contact the atoms in the table. They get close, within a few angstroms, a few tenths of a nanometer, but they never actually touch. The repulsive force becomes strong enough to stop your hand long before any physical contact occurs. When you stand on the floor, the same thing is happening. The atoms in the soles of your shoes are being repelled by the atoms in the floor's surface. Electromagnetic forces are supporting your entire body weight. Gravity pulls you down. Electromagnetic repulsion between electron clouds pushes you up. The two forces balance and you stand on what feels like solid ground. But at no point are your atoms making contact with the floor's atoms. You're floating, hovering above the surface by a distance measured in angstroms, supported entirely by electromagnetic force. In a very real, very literal sense, you have never stood on the ground. You've been levitating above it your entire life, held up by the repulsion between electron clouds, separated from the surface by a gap so small that it's invisible to everything except the most sensitive instruments. But the gap is there. It's always there. And it's the electromagnetic force across that gap that creates the sensation of standing on something solid. But electromagnetic repulsion is only part of the story. If repulsion between electrons were the only thing preventing atoms from overlapping, the math doesn't quite work out. Electromagnetic repulsion alone wouldn't produce the kind of firm, absolute resistance that matter exhibits. There has to be something more. And there is. It's called the Pauli exclusion principle, and it's one of the most important rules in all of quantum mechanics. The Pauli exclusion principle was formulated by the Austrian physicist Wolfgang Pauli in 1925. It states that no two identical fermions can occupy the same quantum state simultaneously. That sounds abstract, so let me break it down. Fermions are a class of particles that includes electrons, protons, and neutrons. They're the particles that make up ordinary matter. A quantum state is a complete description of a particle's properties, including its energy level, its angular momentum, its spin, and its position in space. The exclusion principle says that if one electron is in a particular quantum state, no other electron can be in that exact same state. They're excluded, blocked, forbidden from occupying the same quantum real estate. This has enormous consequences for the behavior of matter. When two atoms are pushed close together, their electron clouds start to overlap. Now the electrons from both atoms are trying to occupy the same region of space. But the Pauli exclusion principle says they can't all be in the same quantum state. As the atoms get closer and the overlap increases, some electrons would need to jump to higher energy states to avoid violating the exclusion principle. Higher energy states require more energy. This means that pushing atoms closer together requires putting energy into the system, which manifests as a powerful repulsive force. This force, sometimes called Pauli repulsion or exchange repulsion, is what gives matter its ultimate solidity. It's not just electromagnetic repulsion between, charges. It's a quantum mechanical prohibition against electrons sharing the same quantum state. And this prohibition is absolute. It's not a suggestion or a tendency. It's a hard, inviolable law of nature. There is no amount of force you can apply that will make two electrons occupy the same quantum state. The exclusion principle cannot be violated, period. This is why matter has volume. This is why atoms take up space. This is why you can't compress a solid object down to nothing, no matter how hard you push. At some point, the Pauli exclusion principle kicks in and says no further. The electrons cannot be squeezed any closer because there are no available quantum states for them to occupy. This principle is also why the periodic table has the structure it does. Electrons in atoms fill up energy levels starting from the lowest. The first energy level can hold 2 electrons. The second can hold 8. The third can hold 18. These numbers come directly from how many distinct quantum states are available at each level. Once a level is full, no more electrons can fit. The next electron must go to the next higher level. This filling pattern determines the chemical properties of elements, the structure of the periodic table, the nature of chemical bonds, and ultimately, the entire field of chemistry. Without the Pauli exclusion principle, all electrons would collapse into the lowest energy state. Every atom would have the same size and the same chemical properties. There would be no chemistry, no molecules, no life. The exclusion principle is what forces electrons into different states, giving atoms their variety and making the rich diversity of matter possible. The combination of electromagnetic repulsion and the Pauli exclusion principle creates the phenomenon we experience as solidity. When your hand presses against a table, two things are happening simultaneously. First, the negatively charged electron clouds of your atoms are being electromagnetically repelled by the negatively charged electron clouds of the table's atoms. Second, the Pauli exclusion principle prevents the electrons from overlapping and sharing quantum states, creating an additional powerful resistance that grows stronger as the atoms are pushed closer. Together, these two effects create a wall of force that your hand cannot penetrate. The wall is not made of matter. It's made of physics. It's made of electromagnetic fields and quantum mechanical rules operating across the empty space between atoms. And it's incredibly effective. You could push against that table for the rest of your life, and you would never get your atoms to touch the table's atoms. The forces preventing contact are so strong that they can support the weight of buildings, bridges, mountains. They hold the entire solid Earth together. They prevent stars from collapsing under their own gravity for billions of years. These are not weak forces. They are among the most powerful phenomena in the universe, and they operate at the scale of individual atoms. Let me give you a sense of how strong these forces really are. When you stand on the floor, your weight, maybe 70 kilograms, is being supported by the electromagnetic and quantum mechanical interactions between the atoms in your shoes and the atoms in the floor. The contact area might be a few hundred square centimeters. In that area, there are trillions upon trillions of atoms, each one contributing its tiny share of electromagnetic and Pauli repulsion. Individually, the force from each atom is minuscule, but collectively, trillions of atoms pushing back together easily support your weight. The force per atom is small, but the number of atoms is astronomically large. Now consider something heavier. A loaded cargo ship weighing hundreds of thousands of tons, floating on the ocean. The water molecules beneath the hull are supporting that enormous weight through the same electromagnetic interactions between atoms. The electrons in the water molecules are repelling the electrons in the steel hull, preventing the ship from passing through the water and sinking to the bottom. Electromagnetic forces between atoms are holding up 100,000 tons of steel and cargo. Or consider the interior of the Earth. Thousands of kilometers below the surface, the rock is under enormous pressure from the weight of everything above it, pressures reaching millions of atmospheres, and yet the atoms in that rock maintain their structure. They don't collapse. They don't pass through each other. The electromagnetic and Pauli repulsion between atoms holds firm, supporting the entire planet's mass. Only under the most extreme conditions in the universe, inside neutron stars, does gravity finally overwhelm these forces and crush atoms out of existence, squeezing the electrons into the protons to form neutrons packed together at nuclear density. It takes the gravitational collapse of a star, many times more massive than our sun, to overcome the forces that give ordinary matter its solidity. That's how powerful those forces are. This understanding completely redefines what it means to touch something. When you pick up a cup of coffee, your fingers don't contact the cup. The electron clouds in your skin interact electromagnetically with the electron clouds in the ceramic, creating forces that allow you to grip and lift. When you shake someone's hand, your atoms never meet their atoms. Electromagnetic forces between your electron clouds create the sensation of pressure, warmth, and texture. When you feel the wind on your face, air molecules are coming close to the molecules in your skin, close enough for their electron clouds to interact, and then bouncing away. Each interaction is a brief electromagnetic encounter across empty space. You feel the cumulative effect of billions of these encounters as a breeze. Even the ground beneath your feet works this way. When you walk on a sidewalk, the atoms in your shoes hover above the atoms in the concrete, separated by angstroms, pushed apart by electromagnetic force. The sensation of hard ground pressing against the soles of your feet is electromagnetic repulsion distributed across trillions of atomic interactions. You are literally walking on force fields. Your entire life has been lived on force fields. You've never made direct physical contact with any object, any surface, any person. Everything you've ever felt has been the electromagnetic force acting across the empty space between atoms. Think about what this means for something as simple as sitting in a chair. You feel the chair beneath you. It feels solid, supportive, real. But what's actually happening is this. The atoms in the chair's surface and the atoms in your clothing or skin are approaching each other. As they get close, electromagnetic repulsion and Pauli exclusion forces build up rapidly. These forces reach an equilibrium with the force of gravity pulling you downward. You settle into a position where the upward electromagnetic forces exactly balance the downward gravitational force. And there you sit, suspended by invisible forces, hovering above a surface made of atoms that are themselves mostly empty space, supported by nothing more than the interaction of the electron clouds and the rules of quantum mechanics. This picture of reality, matter as mostly empty space held in form by invisible forces, extends to every scale. The structural integrity of a skyscraper comes from the electromagnetic bonds between atoms in steel and concrete. The hardness of a diamond comes from the specific way carbon atoms share electrons in a rigid three-dimensional lattice, creating exceptionally strong electromagnetic bonds. The flexibility of rubber comes from the way its polymer molecules are connected by weaker bonds that allow them to stretch and recoil. Every material property you can name, hardness, softness, elasticity, brittleness, tensile strength, all of it comes down to how atoms interact through electromagnetic forces and quantum mechanical rules. The atoms themselves are mostly empty. The properties of materials are determined not by the atoms being solid or packed tightly, but by the nature and strength of the forces between them. This raises a question that strikes at the heart of how we understand reality. If everything is mostly empty space and forces, what exactly is real? Is the table real? In one sense, absolutely. It supports objects placed on it. It occupies space. It has mass, color, texture, temperature. It's as real as anything gets in everyday experience. But in another sense, the table is a persistent pattern of forces maintained by atoms that are themselves mostly nothing. The solidity you feel is electromagnetic resistance across empty gaps. The color you see is the result of atoms absorbing certain wavelengths of light and reflecting others. The temperature you sense is the average kinetic energy of the atoms vibrating in the material. Every property of the table that you can perceive is a macroscopic manifestation of atomic scale physics. The table is real, but its reality is different from what your senses suggest. Your senses tell you the table is a solid, continuous, filled-in object. Physics tells you it's a vast collection of nearly empty atoms held in formation by electromagnetic forces and quantum rules. Both descriptions are correct. They're just operating at different scales. There's something beautiful in this. The universe has figured out a way to build what feels like a rich, solid, tangible world from components that are overwhelmingly empty. Atoms, which are more than 99.9999999999999% nothing, combined together through electromagnetic forces and quantum mechanical principles to create rocks and rivers and trees and people. Emptiness creates solidity. Nothing creates something. The void, structured by forces and rules, becomes everything you've ever known. And think about this. Right now, as you listen, your brain is processing these ideas. Neurons are firing. Chemical signals are traveling between cells. Electrical impulses are racing along nerve fibers. All of this is happening through atomic scale interactions. Electrons are being shared between atoms in neurotransmitter molecules. Ions are flowing through protein channels embedded in cell membranes. Quantum tunneling is occurring at enzyme active sites. Your ability to understand the emptiness of atoms relies on the behavior of atoms. The atoms in your brain, mostly empty, interacting through forces across empty space, are producing the thought that atoms are mostly empty and interact through forces across empty space. There's a deep circularity there. Matter is contemplating the nature of matter. Emptiness is understanding emptiness. Atoms are thinking about atoms. And let's come back to where we started. You held up your hand and looked at it. It seemed solid. It seemed substantial. It seemed like a real physical thing made of real physical stuff. And it is all of those things from your perspective. At the scale of everyday human experience, your hand is as solid as anything gets. But now you know what's underneath that apparent solidity. You know that your hand is made of roughly 7 octillion atoms. Each atom is about 1/10,000,000,000th of a meter across. Each atom is mostly empty space, with a tiny nucleus containing over 99.9% of the mass, surrounded by a probability cloud of electrons. The nucleus is 100,000 times smaller than the atom. If the atom were a football stadium, the nucleus would be a marble at the center of the field. And the sensation of your hand pressing against a table, the feeling of solidity and resistance, is not matter touching matter. It's electromagnetic forces and the Pauli exclusion principle operating across the empty space between atoms, creating the illusion of contact where no contact exists. You have never touched anything. You never will. The atoms in your body will never make contact with the atoms in any other object. Everything you've ever felt, from the warmth of another person's hand, to the coolness of water on your skin, to the texture of fabric between your fingers, has been mediated by forces acting across gaps that are tiny by human standards, but vast by atomic standards. Your entire experience of the physical world has been an interaction of force fields, not materials. And yet, here you are, solid enough to stand up, substantial enough to pick things up, real enough to exist and think and wonder and question. The emptiness inside your atoms doesn't make you less real. If anything, it makes you more remarkable. Because the fact that the universe can build something as complex and as wonderful as a human being from components that are almost entirely empty space is one of the most extraordinary things about reality. The universe didn't need solid building blocks to create a solid world. It needed forces and rules, electromagnetic attraction and repulsion, the Pauli exclusion principle, quantum mechanics, the strong nuclear force holding nuclei together, gravity pulling matter into planets and stars. With these tools, the universe built everything. Stars and galaxies and planets and oceans and mountains and forests and cities and you. All from atoms that are overwhelmingly nothing. So, the true scale of a single atom is not just about size, though the size is staggering. An atom is 10 million times smaller than a millimeter. You need 500,000 of them to span a human hair. A single drop of water contains a number of atoms that rivals the stars in the observable universe. If you enlarged an atom to the size of a blueberry, the blueberry would become the size of the Earth. The true scale is also about what's inside. An atom is a cathedral of emptiness with a speck of matter at its heart. The nucleus is 100,000 times smaller than the atom it anchors. If you removed all the empty space from every atom in every human on Earth, all 8 billion of us would fit in a sugar cube. And the true scale is about what holds it all together. The solidity of the world you experience is not made of stuff. It's made of forces. Electromagnetic repulsion and quantum mechanical exclusion, acting across the vast empty spaces inside and between atoms, creating the firm, tangible, unambiguous reality you navigate every day. Everything you've ever touched, you've never actually touched. Everything you've ever stood on, you've been hovering above. Every surface that's ever supported you has been a force field generated by electron clouds, repelling each other across empty space. The atom is the fundamental building block of everything you can see and touch and feel. It's what the universe chose to build with. And it chose to build with something that is almost entirely nothing. The fact that the universe succeeded, the fact that it created stars and planets and life and consciousness from building blocks made of emptiness, should fill you with wonder every single day. Because right now you're sitting in a world that feels completely solid, held together by forces you can't see, made of atoms you can't feel, built from a void that somehow became everything. The next time you press your hand against a surface, pause for just a moment. Feel the resistance, feel the solidity, feel how real it is, and then remember what you now know. That feeling, that sensation of solid contact, is a conversation between electron clouds. A quantum mechanical negotiation happening across empty space, trillions of times simultaneously, everywhere your skin meets the world. You're not touching the surface. The surface is not touching you. Forces are doing all the work, bridging the gap between atoms that are almost entirely nothing, creating the most convincing illusion in nature. The illusion that the world is solid. It's not solid. Its forces and emptiness arranged so perfectly that it might as well be. And honestly, that's even more incredible than if it were solid, because it means the universe doesn't need substance to create reality. It just needs rules. And from those rules, from forces acting across voids, from quantum mechanics governing probability clouds, from electromagnetic fields repelling and attracting across the emptiness inside atoms, everything you have ever known has been built. Every mountain, every ocean, every heartbeat, every thought, all of it, from almost nothing at all. Thank you for joining me on this journey into the heart of matter. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of how the universe works. And remember, the next time you look at your hand or press your feet against the ground or feel the weight of an object, You're experiencing one of the universe's greatest achievements: the creation of a solid, tangible, beautiful world from building blocks that are overwhelmingly, staggeringly, almost entirely empty space. The world is not what it seems, it's far stranger and far more wonderful. Good night.